of volume. Let S be a solid in the space. So what do we have? We have an object. Okay, this is an object in the space. We're interested in finding the volume of this object. What are we trying to do? We're trying to take a look at the cross-sectional of this solid. Okay, a cross-section of this solid. It's going to be this little piece here, cross-section, and then this guy has an area, all right? So the area of this cross-section, so this is a cross-section of solid S. We can continue this process. We can find this area, this little area, then another cross-section here, another area. They're very close to each other. The second area here, another cross-section. Of the solid here. So we take this area, and we start cutting or finding the rest of these cross sections and adding them all together. Mathematically, we can write it this way. You can say that, hey, the volume of this solid is equal to the Riemann sum. So remember that as long as we are dealing with the summation, we have the Riemann sum of A of x delta x. Okay. So since we're dealing with some representatives of x values, we're using x sub I. Sometimes we can use just the middle numbers, putting a star on top of x, but this I ranges between 1 to n, and then we start taking the limit as n goes to infinity. We are making these very close to each other. Subintervals are getting closer and closer, and the volume turns to be the definite integral of A of x dx. This A of x, these are the areas that depend on x values. So as long as we have the area formula, which is a function of x, we can easily calculate the volume. Okay, give us an example. This example says, find the volume of the solid obtained by rotating about x-axis about x-axis, the region under the curve, y equals to square root of x, as x is bounded between 0 to 1. Okay, well, so what do we have here? First of all, we have a region bounded between the curve y equals to square root of x and x-axis, while x is bounded between 0 and 1. Let's take a look at the graph together, understand the behavior here. We have our x-axis, we have our y-axis. Y equals to square root of x. We all know that the graph is like this. This is y equals to square root of x. My x is bounded between 0 and 1. Okay, 0 and 1. And this is the area that I'm dealing with. This guy says you take this area and start rotating this about x-axis. So just keep rotating this guy about x-axis. The rotation about x-axis. So it means that it creates a solid, and we are interested in finding the volume of this solid. We all know that the volume is equal to the integral a to b a of x dx. But what is a of x? A of x is the cross-sectional of this object. If we can formulate a of x, then the rest is easy. But how do we find a of x? What is this area? If we look at the cross-sectional of this solid, what is it look like? The cross-sectional of the solid, so let us just use plane to take a look at this cross-sectional here. So it seems like I'm dealing with a disk which represent the cross-sectional of this solid. Area of a disk, okay. Of a disk, which is this guy here. But how do we find the area of a disk? What was the formula? The formula was pi r squared, am I right? So a of x is pi r squared. But what is r? What is the radius in this case? The radius in this case is given to me by using the function y equals to square root of x. At this point, we can use y to define r, so we get pi times square root of x squared. So a of x is equal to pi x. A of x is equal to pi times x. Now that we have a of x, we can easily calculate the volume. Okay, so the volume is equal to integral 0 to 1 pi x dx. Pi is just a scalar, it's just a number, so v is equal to pi integral 0 to 1 x dx. V is pi x squared divided by 2. X is bounded between 0 and 1, so we get pi over 2 as the volume of the solid by rotating y equals to square root of x around x axis. So all we have to do is to find the area of the cross-sectional of this solid in the space. One more example. Okay, well, let's go over another example. So this example says, find the volume of the solid obtained by rotating the region bounded by out. About the y-axis. So now we're changing that from x-axis into y-axis. The region is bounded by y equals to x cubed, y equals to 8, and x equal to 0. Okay. Okay, what's the graph like? Let's take a look at the graph together. Here you have x-axis, you have your y-axis, y equals to x cubed. This is y equals to x cubed. And then you have y equals to 8. Y equals to 8. Suppose y equals to 8 is just right here. And x equal to 0. So we're trying to take this region here, bounded between y equals to x cubed, y equals to 8, and x equal to 0, and rotate this guy about now y-axis, not x-axis, just y-axis. So what are we trying to do? This is my x-axis, this is my y-axis, and this is the rotation about y-axis. Y equals to x cubed. Taking this guy and start rotating this. Just change this so you see we have x cubed. We're taking this guy and start rotating this region, and then on top it's bounded by y equals to 8. Well, okay, so as usual, we need to find the area, the cross section. So the volume is the integral a to b, the cross section, the area, and if it's dependent on x, we have area with respect to x-axis and dx. Okay. Now just think about this. Are we trying to rotate this with respect to x-axis or with respect to y-axis? Well, isn't that easier to take the integral with respect to y-axis while your y is bounded between some values and this area is a function dependent on y? In another word, we're finding the volume while y is bounded between C and D, and your area is a function dependent on y. So you're finding the volume of the solid. We're taking this solid and start rotating the solid with respect to y-axis. So another formula using variable y instead of variable x to help us calculate this volume is v equals to the integral while y is ranging between c and d. The area is a function of y with respect to variable y. So your job is to find this cross-section area. What is this area? And then plug that in here. Just start taking the integral. The job is to find this area. What is this area? Very well. Let's take a look at this disk here. This is a disk that you have. Well, okay. This is my disk. And I'm trying to find the area of this disk. So I need the radius. What is the radius here? The area is not that hard to find. The area is equal to pi r squared. As long as we have our r, then you're done. Just note that you're writing this area depending on y instead of x. So take a look at this function. It's y equals to x cubed. What's the meaning of that? If I take the third root of both sides, x is equal to the third root of y. So my r is equal to the third root of y. So my area, A of y, is pi, the third root of y to the second power. Now the volume is equal to the integral. But what are the values on y-axis? What is C? What is D? Well, it starts at the origin, so from 0, and it starts at top, and I know y is equal to 8. So y is in between 0 to 8. A of y, or the area, is pi, the third root of y squared, dy. This is not that hard. Taking the integral 0 to 8, pi, here you have y to 2/3 dy, so volume is pi 1 divided by 1 plus 2/3, y raised to 1 plus 2/3, and y is in between 0 and 8. Again, I'm not really worried about 0 because this guy is going to be 0. The only thing is 8, and we need to plug that into the volume formula. Okay, V is equal to pi times 3/5, And here I have 8 raised to 5 thirds, which is 2 to the 5th, which is 32. So I get 96 pi over 5. There we go. Let us make it more interesting.